1, 2, 3. This works. Now we just need music. 1, 2, 3. This works. Now we just need music. So, hello everyone and welcome to the next live stream where we want to work a little bit further at our maze AI that we created. If you haven't been here the last time, or if you don't know anymore what we wanted to do, as you can see we can create a start point and an end point. And I hear myself, I shouldn't do that, just a second. If you haven't been... Perfect. So that means exactly we can set up a start and end point in our Flutter app, and what we can also do is we can create walls. And the idea is now that we can create a search algorithm that finds the easiest way from this point to this point and make it visualizing, so that we can see which section of the app or which section of the fields has been checked and where it goes first to identify the best path. So that's the goal for today, and I want to go further with this. Just checking, the bitrate looks weird. Do we get any infos? Nope, looks good. Hopefully you can hear and see me good. Okay, water is prepared. Maybe a quick overview what we have done the last time. I have this now in the emulator from iOS. We could also start that up in macOS desktop, which I probably will also do because the performance is a bit better. And we were the last time that far that we implemented our DFS, so for deep first search. And this deep first search, we want to check the cells and we wanted to find all the walls, all the paths. And yeah, we wanted to implement them in an order, and then we can start by clicking on this start search. So kind of like this, I just create a quick maze for us. Nope, that wouldn't be working because then we will get the information that we cannot do that. And in order to make the search algorithm a bit easier or a bit faster, I just make just one path at the end. So like that. So I shouldn't be too creative because I don't know if this is anywhere working, but kind of like this would be the end result. Okay, so how can we identify all the walls that we have in our array? So how did we even implement everything? So you can see we get a list of cell states. And the idea is actually, if we go here to home, that we have down here a list of cell states, and each of these cells has its own cell state. And this contains, if I know exactly just the values, hey, a placebo, nice to see you. Great, already 2 followers, daily done, so we can leave. So the idea is every of these cell states has a wall, path, start and end. And what we need now is the information here from all walls, which identifies the index from all the walls that exists inside of this array, 2-dimensional array. So, and how can we identify that? Well, we have to go through each wall, through each cell, and check if the state is actually a wall. So for we want to go through each cell. So what we could do is just making this, and now here inside the element dot we have an index, but the element itself, we can now check for if it is a wall. So if element equals to cell state.wall, and if this is a wall, then we want to add it to our list up here. So that means all walls dot add, and now we have to identify the element index. All right. So, and just to see if this worked, we check out the all walls here. And let's run this part and just see if we get the right result. So all walls plus the all walls. Like so, just to make sure that we see where it comes from. And if I press now start search, we should see in the runner, hopefully not an error. Add was called on null. Sure. So the all walls is at the moment an empty list or a null. Now it should be better. Oh no. So I made hot restart, which was a mistake. We need this, and say start search. So we can see all walls is now an empty list. So it seems that we couldn't find that. So element, hey debug, very good to see you too. So now the question is, do we find even the right elements here? So if I start the search, we go through all, path. Yeah, sure, I don't have added any walls. So that makes sense that we don't find any. So if I make the easiest maze possible, start search, go to the run. Yeah, but now we have a lot of zeros, which is also not correct. Does the for each method return the index? No, unfortunately not. Could we get somewhere the index? So if we have for each with index start. Iterator index value. For each index value. As map. Okay, so we can use that, I guess. So if we say here dot as map, and then we use the for each, then we receive the index and the element, and then we could just add the index here. So let's see if this works. Start 1422, and now let's check if this works even. So we have here 8, right? So 16 I think we start with 0, right? So 8, 16, and this one is 14. Then plus 8 is exactly 22, plus 8 30, plus 8 83. Yeah, perfect. So the numbers are correct. With that we have our walls. And can we also search for paths? So I think we could also do that here inside. So we add this all paths up here. And what we need to do is checking here if the element, so we can make a switch maybe where we pass the element inside. Now we can say if the case is a cell state.wall, then we make this part here. And else we have the case cell state dot path and path. And yeah, so then we have the all paths, add the index and break. So they will add also the start and the end, but do we actually need that? I think we added that already in the beginning, right? I think we need one more thing. We need to throw an error if start and end is not set. And what we can do instead of using these two, we could pass in that down here to make it a bit easier to read. So cells index of cell, so we could just say start is a number. Let's break here at the moment just. Good, fair enough. And find all indexes for path and wall that we have. And here I want to say if start is, what is index of if we don't find anything? I think -1 return, exactly. So the start will be -1, or this way, the end is -1. Then we want to throw argument exception or argument error. And what we want to say, it needs a start or end date, start or end position. Good. Okay, so what that means is if we restart our app and we get our empty state and I wouldn't add something, then we will throw now an error. Invalid. It needs a start or end position. We don't really identify which one now, so the user has to figure out. We could of course improve that, but I think that's fair enough for now, for our minimal value MVP. Good. So that we have this in place, we have this wall that can be gone. We don't need that anymore. We have our walls, our start and end. Can remove these too. All right. So what we did the last time too was we will compare it to our solution that we received from the edX. If you haven't heard about that, the last time already announced that I do at the moment the AI introduction course from edX and the Harvard University, which is completely for free. So everyone can join there if you want. This introduction to artificial intelligence is completely for free. And it's really good with a lot of information about how everything works. And you can see that we have projects, you have quizzes for each stage and so on and so forth. And we are currently working on the project 0. But what I did is I did try to transfer the knowledge from the AI course into Dart and Flutter so that we can, or that I really understand what I'm doing here. And at the moment I took the source code, I guess. Yep, so we don't have to download it again. And I just keep trying to identify what they have done with the whole thing. So as you can see, they keep track of the walls. They have now a 2-dimensional array. So they have used rows and columns, or columns and rows to identify the right places. And yeah, we do it a little bit different because we have just a 1-dimensional array, which just goes through all the lists at the moment. Maybe we have to improve that in the future. Good. And one last thing that I see here seems that we have figured the row which gets added to the walls at the end. And the walls are false or true depending on which way they go. Is this correct? So this sets the goal. And as you can see, they always send a tuple of information like I and J. Oh, my stream has broken down. I hope you can still see something. Quickly reload. Yeah, okay. All right, so they always send a tuple with I and J, and of course we cannot do that. So instead of using a tuple, we just use the index of the array where we are at the moment. And in order to get the states that we can reach, so if we, for example, are at this location, we can go up to the right or to the top. And to receive them, we will have to use this position. -8 would be this position, and this position +1 would be this position. So we have to just keep that in mind if we solve that later. But what I want to do is I want to follow now more or less this solve part here. So here we can see we have this num of explored levels. We have a starting point with a node that we created the last time. We created a frontier, we add some start positions, and we have some explored sets and so on and so forth. So let's try to bring that over into our application. To navigate inside of our grid, you see there I was writing the reminder for us, and now I want to start with the DFS. So let's hope that everything works and we can use that. So first we start with the a number of explored tiles. Can I write here? Is everything okay? Looks like we have some problems here. If you have any questions in between, just ask, right? I'm more than happy to answer them. Okay, so explored tiles that we have, then we have the start node. That is the node where we begin. So this will be the green point. And therefore we have to set the state inside. So self start. The start is a tuple, if I see that correctly. Yep, so it's this position where it starts. For us, this is just the index. And it has, of course, no parent and no action. Good. So for us, that means we have the start. This is a node, start node. And I think we can do it correctly, like so. And we create a new node, which we have to import, I guess. Yep, from the utils folder. So we created that already, this class node. And as you can see, we have a cell state here. That is the state, but this is actually wrong. This is just a number or an integer. And hopefully here is still everything okay, but here we get the problem, I guess. No, it's also okay because we don't use it anywhere yet. Good, so at the moment this has no constructor, and I think this is something we should change. So let's make this final here quickly. And with that we can create a constructor very easily. And as you know, we want to have some of these null. So in this case, we want to surround that as a named parameter part. The only thing that always have to be something is the state, but I keep it for now like this. The parent should be also an integer, because also the parent is a tuple at the end, I guess. So let's see if we find somewhere else where a node is created. Down here. And as you see, we have the parent. No, the parent is a node itself. And action is anything. Okay, interesting. So that means for us, the parent is a node itself. Oops. Perfect. Okay, so how does it look like? We want to set here something, and the state, as I said, is the state of the first tile. So we have to pass in start. And if you don't know where the start comes from, this is this number from index of that we received where the cell start is. Then we have the parent. Obviously we don't have to set that because it's automatically on null, so it makes no sense to set them. And I think in order to create a node, we always have to pass in a state. So that's why I will add that now out of the state named parameters. And this is our start state. Don't know. No, I think start was good enough. Okay, so we have our start node, and how do we go further? The next step would be to add the frontier. In our case, if we want to use a DFS, which we do here in this case, we use the stack frontier. If we would use the BFS, we would use a queue frontier. The difference is a queue is we start always to take the last element that has been no, wait, slowly. So a stack frontier means that we put always something on the stack and we take the first out. So that means first in, last out, right? First in, we put more and more in, and we take the last always out. Yeah. So first in, last out. If we do a queue, we do it's a little bit different. We put stuff inside, and then it's like a queue in a line, right? So we put something in, and the first thing that we added gets left again. So that is very important to see the difference here, because with that we will change the whole behavior of the frontier. Okay, so let's create one. This is DFS, so we use stack frontier in our case. This is a stack frontier equals to a new stack frontier, and that should do the trick already. Okay, next we want to add our first node to the frontier, and they just named it frontier, so I will do the same. And we add the first node here, that is our start node. Good. So with that we initialized our our frontier and added the first node. Explored, that means we have a node which is already explored. So that means that we don't have the possibility to move back to our last node. So for example, we would be here. We go, for example, I draw it now with a path. So we would go here and would check that. Then we could also go back again, but this makes no sense, right? Because then we would just go back and forth without solving our problem. So we want to make sure that we keep in track where we have been already. So that means we need an explored flag, which is a list of indexes. So a list of numbers at the end. So we have a list of num where we have our explored list. And this is an empty list, or in this case it was even a set. That means everything that inside needs to be unique. And the set is created like this. Okay. So now we are looping until we find a solution that makes sense, right? We want to get finished somewhere, so while true. And then we are running through each element inside of our node list. So how does it work? The first thing is if the frontier is empty. So at the state where our frontier don't have any more nodes to explore, we are done. Something don't work anymore. So that means, for example, if we would be here, we can just add the starting node. After that, we don't find any node that surrounds this node. And with that, we would be done and we can throw no solution. We know that there will be no solution in our frontier. So what we can do is then say if the frontier empty, I think we have, yep, frontier is empty, then we can raise. And in our case, it is throw, because if you don't know this programming language here, this is Python. Okay, so we throw also an argument or an exception that there is no solution. Good. Makes sense so far. Now we remove one node out of the frontier. That means if we have a stack, for example, we put stuff inside, and now we take the first element outside and check everything on that node. And in our case, at the moment, there is only the start node. So let's take that out to identify what we want to do with it. So we have a node, and we use our frontier where we remove the first element. And if you don't remember this method from the last time, we first check if the frontier is already empty, and if not, then we return the last element from the frontier. And this is also the difference to the queue frontier. It is the only method in the whole thing that actually changed. You see here we remove the last element from the list, and down here we remove the first element of the list. Okay, so far so good. What's next? The next thing would be to increase the num explored. We check the state if we are already at the goal. Okay. And if we are at the goal, then we found our solution, right? We are done. And else we mark the node as explored. Okay. So let's get into it. We have our node, and the first thing was if the node.state is equal to the goal. Or I think end is it for us. So then we can write here to do, finished, and have a solution. Good. And the last part that we can do, so I just jump quickly over that, and we take down here a little bit on the eye, because this is the finished goal, right? But this part here actually is we go from one node to the next. And I think, yeah, so that would mean we first mark this node where we are at the moment as explored, which makes sense, right? So explored dot add, and here we add the current node. And the next thing that we have to do is this part here. So what happens is we call this method called neighbors. And if we take a look into it, we get from the current state, so where we are at the moment. So you see, this is the node state which we get at the moment. And what happens, it calculates the different candidates that we can have. So up, down, left, right. And this always is the value from the, as you can see, up is in the same column, but in the row we go one minus. So we go, yeah, we are staying in the same column, but we go one row up. If we want to go down, we let's say we would be at the beginning. Where's the starting? So we will be here. So down would be the same column, but one row down. So this part here. For us, that means we have to calculate that a little bit different, but that's fair enough. We can quickly and easily do that actually, or I guess we should be able to do that. So let's see how we can do that for us. So first of all, I call this method in the first place a little bit different. Neighbors, oh, on the other hand, neighbors could be a good name for a method. Not sure, but yeah, let's keep a helper method called neighbors. What does it actually return us? It returns us result, which is a list of actions and the point where we want to go. So the action is up, down, left, and right, I guess, and this is the tuple where we can go. So, all right, so let's see where I can add them, where it makes sense. So this is the search controller implementation. Yeah, maybe a private function would do the trick. So we will return a list of different actions. So list of actions, or list of action would be maybe a good name. And neighbors. Well, this gives a typo, I guess. Neighbors. No, it's right. Okay, and this will return something for us. And this is a private method yet. Hey, Minu, nice to see you. Hope you are good or healthy and happy. So, I do somewhere a mistake. That's odd. This is the start DFS. Okay, and I want to create a function here, list of action, for example, or yeah, let's keep it like that. Say neighbors. Neighbors. And this is a method that we want to call with a state, a certain, and we return a set of, I think a set would be better. No, what we could do is having a map between a string and a number. So, and why is it a map with a string and a number? Because the string is up, down, left, and right. That would be state.value, right? What is state actually? We come here with the state. This is a number itself. And for example, we have up. So if we have this position and we go up, that would mean we take this position from the index and remove 8 of it, right? As virus. Oh. Sounds quite dangerous, Minu. What are you doing? Can you fix it, or did it already destroy your machine? Sorry to hear that. So yeah, we are here and we make -8. So it is actually the state -8. Then we have down, which is the state +8. Then we have left, state -1. And we have right, state +1. So the only thing that I don't know at the moment is what happens if we are at the corners. So let's check how they do that, and they check for action in candidates if 0 is smaller than R, is smaller than self height, width, and not self wall. Okay, so they check if it is even existent. So R is a point somewhere. It cannot be smaller than 0. It cannot be higher than the height. And so because they have a 2-dimensional array, right? So they check against this. And so this is also more dynamic, actually. So maybe in the future. All right, that's the spirit, Minu. Very good. Okay, but as you see, we then just append it to the result where we have the action. Because we get that from the candidates. Okay, I see. It's just a check that we want to do. Okay, so we have to do the same thing more or less. That should be a bit easier for us, I guess, because this would be the result map of string num, and this is the result, like so, I guess. And what we want to do is now checking all of these result elements. So how can we do that? The easiest way. I think we can say result for each. And now we receive the key and the value. And this is nearly the same as this, right? The action is our key and this part is our value. Now we don't need this part because, or at least not in this way. We just have to check if we are still in the array. So let me think, how can we do that? That means the value. So if the value is larger than 0 and the value is smaller than, I think 64 is at the moment our highest part. So if this is the case, and what is important is now we would have, or it would be great to have also access to the cells, right? So we would have the list of cell states here because, and I will show you in a second why. We want to check the cells if it is a wall, because a wall is not part of it. So it's not possible to go through a wall, right? So cells with the different index, so where it is, that will be the value, is unequal to the wall. So, and now result for each. And I see right now what we could do, and I guess that would be amazing if this works. We can use that and say remove where. Remove where. Let's see if this works. And then we return this. So where, remove where the value is smaller than 0 but bigger than 46. And this is not an AND, this is an OR. And this is also an OR. So if it is smaller than 0, or it is bigger than 46, or it is a wall, it is a wall, then we remove it from the list. And then we just return the result. Okay, that could work. Let's see. So that means down here, we have now added this, we get our result back. And where have we our part with this? This is the neighbors. We get the split lines, we get our results, solution, print. No, where is our solving? Here. So down here, we go and say we get our neighbors with the state, and then we have the action and the state. So at this part, we can get the neighbors with cells and the state. And now we can say entries would give us a map entry or all the map entries. We can make it dynamic, but we want to have it for now as easy as possible. We can do it then in the future and improve it. So at the moment, as you can see, I just made it hard-coded to 64. So it is impossible to have more than this at the moment. In the future we can do that, absolutely. I'm more than happy to do also like that. Because I think it would make sense to add that maybe as a web application somewhere, so everyone can run these different methods and see how it works. But for today, I think it would be already good to at least see how we can navigate from here to here and make it possible to maybe color it so that everyone can really see how the search behaves in the meantime. Okay, so explored, add node state. Where have we been? Exactly, so we want to access the neighbors. And now we receive the cells, that's good, and node state. So from the current part we receive the neighbors, which is a map of different possibilities, right? Let's see what happens here next. And state not in self-explored. No, that has nothing to do with it. We receive the action and the state. Can we actually do the same thing here, like action and state, and say in? Not like this, of course. We have to do it like that. Nah, it's not possible. No. But that's no problem. What we can do, of course, is we can say for each here in this case. And because we receive now the key and the values, because it's a map, the key is our action and the state is our value here in this case. So we can call it also state. So these are all the states from our neighbors. And if not frontier contains state, if not frontier contains state, so if the frontier does not contain the state and the state is not explored already, then we add it to our frontier list. Okay, so if the what did I say now? So if the current node is not part of this the already explored ones, right? So the state is not part of the current explored. Wait, explored contains, and now we say the state, and well, I think we have to say not. If it is not yet explored, oh wait, explored is from, no, it's correct. No, that's fine. Okay, and the other part have been, and state is not in self-explored. Ah, and the frontier, I forgot about the frontier, of course. Contains state, and now we pass in the state. And here's important, this is now a dynamic, but actually it's a number. Yeah. Could be even an integer. Good. Here we want to do something. So if this is not the case and this is not the case, then we create a new node. So this means node equals, or var node. And now we have to pass in the state itself. Hey, Gladlim, hey! Good. So we have the state, now we have the action. The action is our action, our key in our case, right? So this is our action. And the last thing we have is the parent, and the parent is the node that we are currently on, so the node. And we should maybe change the name here, which is the new node or child node or something. Good. And frontier.add the child node. Good. Frontier add, we have the state added here, the parent is the node, and this is called child. Okay. Fair enough. So this is that part. So now let's read the goal again. So the actions are empty. No, is a list. The cells is a list, and we go through all the node parents that exist until it is not none anymore. And then we add to the actions and the cells all the nodes, all the actions and states of the different nodes. And then we reverse everything and have a solution. Okay, so that means also here we have actions and we have, this is a list of strings that will be up, down, left, right, and so on and so forth. And then we have a list of, what was the other thing? States, so numbers probably. Have limits that don't require to have dynamic variable. Yeah, but I think Minnow is right, because what we could create is like a very infinite sized grid where everyone can draw as much as you want. But yeah, that's future music. But it's a good idea at the end. Let's see how we can solve that one by one. And here it is cells, where we add the different states. Okay, so this is num, which we can call, no, cells is not a good name because we used that already. On the other hand, maybe we can use it once more. I'm not sure. That worked. Okay. So then while our node.parent, so from the current node, that is the goal node, we search while this parent is unequal to null. Can we here check something? No, unequal to null. And now what we want to do is appending to them the different state and action. Okay, so actions.add action typo dot add node.action. And then we have the cells.add node.state. And the last thing was change the node. Yeah, of course. So node equals node.parent. Yeah, I thought exactly the same, to be honest. I want to make a whole week of live stream, but I don't know when or how I find the time for that. It would be so cool. Actions.reversed, and that makes sense because currently what we would do is we would go from the end to the start, but what we want to have is the start to the end, right? And the other thing is that is the actions and the cells.reversed. We would set the solution, I guess. Yep. The solution is actions and cells, so we create a new array probably from the two. Okay, interesting. Not absolutely sure how this would look like in Python. I think it creates a tuple with two lists, right? So, is it possible to create tuples in Dart? I'm not sure with that. Tuples Dart. Let's see. Oh, there's a package for that. Const tuple string A10. Okay. So if we need a package, I think that's not the thing. No. You use it, yeah. And happy with it? On the other hand, why not? I think it's very easy to install it. So we can do the same thing. So pubspec.yaml and add it to the dependencies here. Go, make pubget. So, and as I see it here, it should be pretty easy, right? It's just a tuple, the value of amount of how many tuples we have. And then we just say what type it is. So in our case, to return that, we would create tuple2. And this would be a list of string and a list of num, like so, which is equal to, no, we created. So with that, and then actions and cells. And this is our solution, right? So, how can we set up the solution in a good way? And why do we need this part here? I think I forgot that somewhere to add the explored tiles. So num explored, where it's also, it's here. So whenever we remove one, we have also to enhance this number here. So that would be here, I guess. So let's make it the easiest possible way, I guess. But this was at remove, right? This is an add. Where's the remove? The remove. Should be at the beginning, right? Frontier add, frontier empty, frontier remove here at this place. Good. So we have this tuple, and this is our solution. And at the moment, we don't really have a good place for our solution. So with that in mind, I just return it at the moment. And the method is complaining. For what do we need this explored tiles anyway? Oops. It's getting exposed at the end. Okay. Then I will add that here too, which is our explored tiles. Import library, of course. Can't be returned from the method because it has the return type search result. That makes sense. Hey Stefan, nice to see you. Interesting. Yeah. Because I knew that there wouldn't be a tuple, I created this this search result here. And that makes, of course, not so much sense. This is just a state that it can have been, but actually this is always a tuple free in our case now. Up, import it like this. And here, of course, we have to change them slightly. And here we go. I think I have to set that also to 0. And by the way, that leads me to a thing. Maybe I can do that from here. So this way. Perfect. So my good old moderator's back in place. So with that, we should be able to run our application and see if everything works. At least we should get now an information back to our home view where we actually initialize that run. So we start the different things. We go here, start DFS, and at the end we should get back our tuple free. And the tuple free would be like DFS result in that case. Let's see. Don't make it too complicated. I actually just want to print a little bit. DFS result dot item free. Do I have to set up the... wait, I think I should make that a bit more clear what I return here. So this returns a list of forgot it again. Let's see. So this part, string, list of string and numbers. Yeah. Hep and hep. So. Good. Okay. So I will restart that. We will click here and we will click here, and now I can make a maze. Kind of. Very complicated one, as you can see. Close that, make your path. And start. Do we get something back? I don't see an, I see an error. Fantastic. Invalid value, not an inclusive. Yeah, okay. All right, so our first bug appeared, and that's the reason why I should have written tests, right? Because then we wouldn't run in something like that. So if we see, at the moment I talked about 64, but it's actually one less. And I think this here can be smaller or equal to null. No. Okay, let's try it again. Oh no, I shouldn't do that. Okay, let's create again this, and then we do it this way. Start. Broken. No element. No element. Untap, send tab down, and then we get no element inside of the implementation for each neighbors. So we tries to access this somehow. And he says no element. The problem is this here can be null, and then he tries to access for each, of course. So let's try it with a question mark. But the question is why he's even coming here. So start search. No element. Print result. So we get left 55 and right 57 from here. It would be good to have the starting location, so I give also the state. So, and start. 65. So it says that it can go down up here. Okay, I see. The problem is that -1 is not really working, right? If it is modulo 8 or something like that. So if it is the first of modulo 8, it cannot go to the left. That's not true. And if he tries to go one left, actually it should find the problem then too. So no element. Collection list, controllers. Does it mean we don't come here inside? For the first one we come inside, so left works 55, and then it says no element somewhere. So the right, he finds right, but he tries to go left first. And if I write that a little bit different just to get the understanding here, that would be a map entry. Is it a map? Yeah, a map entry. Map entry. Entry in neighbors of cells and the node state. Does that not work? String num. Used in for loop must implement iterable. Okay. Ah, yeah, because this is a map and I have to get all the entries, I guess. So let's see, we get the entries. And 4. And now we can say the entry in. Good. And this entry has a value and a key, and now we have the same thing, so we can get all of that inside here. And this will be entry.act. The action is the key, and this is entry.value. The state is entry.value. Entry.key, and this is entry.value. Okay. No element. Do we have to create a debugger? Interesting. So the left one he tries and then it crashes with no element. Even though that this returns us 2 elements, right? So I will close that off. I will make a breakpoint here and debug. Let's see what we will find. Yeah, I want to work a little bit with AI. I always wanted to do so. So it's great if you can enhance your skills by that. That would mean that I achieved my goal with it. So red and green. Let's put it there. Go and start. So, okay, the first one is 46. No, this is the cell size. We have start at 4, the end at 6. All vaults we have here and all paths, okay. So when I'm looking at the neighbors, I didn't add an own variable for it, so we don't see the result actually. Okay, so let's just let it run quickly and let's see what the result is. No element still. He only can go to the right. This makes no sense. Where does it crash? Inkwell, home view, search implementation. Up here, frontier contains state. Aha, okay. Okay, so this one crashes. First where, and if first where don't find anything, it crashes. So I guess this was the problem for now. So I just say if it is null, so he don't find one, then he should return just null. Return node unequal to null. Ah, yeah. So how do we work here? Up. So actually, Stefan, I don't really explain everything. So I tried to give the hints that I had in my mind. But actually, the most of the stuff comes from the CS50 course that is anyway for free, where you can just participate and get the knowledge that you need more or less to follow completely along. That's pretty cool in my opinion. So that was the idea behind all that stuff. No element still, so still crashing. Contains state. We have a node. What is or else? Yeah, this one returns no element, unluckily. Or else unequals to null, return or else. Okay, is there a function that I have to pass into? Maybe this is the problem. And return null. Maybe that's the case. Ah, we don't have to return here. Like so. There is no solution. Okay, fantastic. All right, at least we have now the right answer. We don't have a solution. We don't have the right answer, but we have an answer. So what happens? He tries to go down, and then he finds 26 and tries to go down once more. Look at that, you can post links into the chat. Isn't it great? So that is this. Frontier first, where this or else is null, return node unequal to null. So, out of reasons, this one is now still wrong. Hoppla. Sorry that I eat something, but if I wait so long, I have to eat. Okay, so the key is right, or the action better said, and the value is 42. That's good. So let's jump over that. Let's jump over that. The explored cannot contain that, right? So we should be happy with that. And it does not contain the state. So we should go to the child node now. Oh. Ah, wait. If explored contains the value, if it not contains the value, and the frontier does not already exist. Ah, okay, this is wrong. So retry the whole thing. Well, at least not for me. I tried my best to implement the feature for linking in the chat. I was really, somehow I couldn't do it. I think other people were more successful with that. So green and red and surrounding it. Go. So there's a lot of chat. It didn't crash, which is good. So we, I think if I remove now a lot of these prints, we maybe get also a better understanding of what we receive. So what do we get here actually? Up, down, up, down. Where do you have me more prints? The active tool can be removed. Print the state, remove where can be removed. So DFS results. So this is the item 3. These are the steps that it took. Steps to solve. Up, up. Like this. Good. Then we want to add here the item 2 just to see how it is solved. So this will be item 2 is the list of numbers that will be the different states that it took, and list of strings would be the values how we moved in the grid. So let's try with the item 1. We can call that the actions. So down, down, and we found steps to solve were 3, so that looks pretty good. Start the search algo. Why do I get this message afterwards? That is a bit weird. Start the search algo. I think we can remove that. Okay. So now we find that, and if we reset everything and I do it here and here, let's start the search. Okay, it took 34 steps, and it took right, up, right, up, right, up, right, right. Oh, right, up, right. It always goes up and right. So it took like, it goes here, then it did go here, and then it goes up here. Okay, interesting. So could we do something? And what I want to do is, first of all, I want to make it a bit slower, and I want to make it colorful so that we can follow along how these two things connected. So how can we do that? We have the cells here that we pass into, and I think this is the same cells that we have up here, right? So if we change, I don't know if we can do that. I have to think about that. So we start the DFS, and what I want to do is, with each step that we do, I want to change the color of the current active field that we are on. So how would we do that? We have this start, we have this end, okay. And now we are starting with all that stuff. This is just to collect all the walls, all the paths. How can we do that? We would have to call the context, right? And re-trigger the build somehow from here. That we could do with a state management solution, or I would like to make it as easy as possible. But actually, I think there is nothing easier than just create a riverpod provider or something where we change the state of the cells. So at the moment we have our home view, which contains our cell state, and here are living our cells. And these cells will be updated, and now our whole part needs to react on that. Yeah, I think we don't come over that. So let's try by easily implement a provider, I guess. That's just the easiest thing I know about at the moment. So let's use the installer. Give me quickly the provider. Now we would also get rid of getIt, I guess. We don't even use it at the moment anyway. We get the provider. And inside of provider, if we take a look at the example, I think that was with the change notifier, right? So let's see. Exactly, they have the counter in that case with the change notifier. We would have like the state of the cells. I will create a folder for that. That will be our providers. And we have our home view provider. Okay, the class home view provider extends change notifiers. Was it just change notifier? Yeah, I guess. Okay. And this home view provider will have certain states, and it will contain all three of them. The cell state, the cells, and the search algo that we want to select. All right. So the biggest issue is that we are not allowed to manipulate them directly inside of here. So what I will do is make them all private, and say we have a getter method. So we return cell state, get cell state, active tool, and return this active tool. Did I do anything wrong? Just like that? Ah, okay. No worries, sorry Stefan. It's always a bit tricky if you come from the middle of somewhere. Here we want to return get this dot cells and not with an underscore. And last but not least, we want to return the search algo. And here we return the selected search algo. This selected search algo. Fantastic. Oops. Ah, getter. Okay, so this were these, and now what we want to do is we want to update them, right? So update active tool will be returning void. It receives cell state, and this active tool equals to new tool. Void Then we want to update the cell with an index and the cell state. Better call that new state. And here we say that we take the cells searching for the index and we update the state. And don't forget, whenever we update now something, we have to notify our listeners. And last but not least is the search algo, which is void update search algo. And here we receive a new search algo. And this equals algorithm. Underscore, right? So cool. Okay, so this is the provider that we have. Here we want to access them now. So the first thing that we need to do is removing the state full widget. That means we will have no cells.add cell path. Ah, yeah. So this will have to be inside of the provider now. This can be gone. So in the search, no, inside of the provider, we will have a home view provider, which creates us that stuff. Good. Now we have here a lot of problems, of course, because we don't have any set state anymore. Can remove that already. We'll access that soon. Or better, we keep this part. This can be done. So we keep them for now. Just first finish off the provider part. So what we want to do is that this home view has access to our provider. So this is provider. Create. And with the context, we create now our home view provider. Was it like that? So just quickly check here again. Change notifier provider, is it in that case? Not just provider. The create still the same, and we recreate the home view provider. Okay, so that creates it, and now the whole home view has access to everything that is inside this home view provider. So, and the rest should be fairly simple. So we have watch, for example, which comes from provider, hopefully. Am I wrong? So where is it? We have the build function. Ah, no, it was context.watch. Yeah. So context. Inside of the build function, context.watch. Do we have to import something? No, it should work directly. Maybe we have to import the provider. So up here we add that. And now here we want to watch, inside of the build function, context.watch. Finally. So, and what do we want to watch for? We want to watch for the file. So this will be our home view provider. And here on that one, we want to have, for example, the active tool. So we can say this is final active tool equals to that. That works. And we can, this is the update function. So what we will have to do here is probably context.read. We get the home view provider. And now we want to access update active tool, and we pass in cellstate.wall. And this can be done, and this we need. So if you don't know the difference between watch and read, with read we only receive the first information, while watch will always looking for changes in it. Then we can change that, and we can change that. And we have to be careful a little bit. So the circle was path, the wall was start, and this was end, I guess. Okay, so now with this set state, we create the different, we recreate all of them. Unpressed. Yeah, okay, this was just to clean up everything. So what we can do is read and create here a reset all function. So, and here in that reset all, we don't have to pass anything inside. And what happens here is that the cell's getting recreated. First cells.clear and then recreate. Okay, inkwell we don't need actually, the search is not our main concern, nope, and the home view. Okay, so reset all, actually we don't have to pass anything, and we don't need this, we don't need this, and this. Can even remove this. So, oh no, somewhere I made a mistake. So we have the unpressed up here, we have the icon button. And build context. So we have the set state. Okay. All right, so next step, we have the cells. To receive the cells, we go up here again because they could change, right? So we have to watch them again. So we get context, watch, we want to get the home view provider, and we get the cells. All right, now we have a set state with active tool. Clean out starting point. So I think we just don't need the set state in this case. Good. The drop down button does not work anymore. Couldn't infer type parameter t. Try to infer dynamic for t, which doesn't work. onChange declared as void function t, but argument is null function search algo. Okay, so let's see. Okay, this part. So selected search algo comes again with the context to read, or better, find final active algo equals to context watch of the home view provider dot selected algo, or let's stick with it, selected search algo. This is now again the update, so we can access the context.read home view provider dot update search algo with the value. Good. And last but not least, down here we also access the cells index of. So because this is now outside of the build function, I guess we have to pass it inside. So we pass in the cells inside. That means we get here a list of numbers, cell states, of course. Good. So hopefully our app is still running. Let's run that in normal. Sorry, that was just a bit refactoring now. And probably I should done that in the first place like so. So hopefully everything works now. So, nope. Okay, so when we change the color, we would not do it correctly at the moment. So if I select something here, we notify our listeners, but it seems that I forgot somewhere. So reset all, notify listeners, of course. And by the update cell, we get a new state and we update it. Print update. So I take a new wall. No, it's not getting called. So update cell is never called. This guy here is it, I guess. So if we tap on a cell, we check if the start and end point is correct. And at the end, we want to update the update cell with the active tool. And I think we have to pass in the current context.read home provider update cell, and we pass in the index, which is the index, and the new state is the active tool. So let's see if that worked. So I select one and I can update them now. Good. Reset all is also working. Fantastic. Okay, but what did I achieve now? The benefit is now we have these contexts everywhere, and what I hope for is that I can change now the behavior on these elements. How would I do that? I can give into start DFS probably the provider. So, so what I could do is give the provider inside, like context.read home page view provider. And let's see if this works like I expect that. No, not that easy. This is cells. We coming from this onPressed method. Do we have access here on the context? We should. Elevated button. And this lives inside of the build function, right? So, unpressed search controller. What I could do is the following. So we have these now 3 times, and I guess it would make sense to replace that to create the kind of this, and then provider active tools. Also replace this to provider cells, and last but not least, provider searched algos. So, and another thing is, if we want to access only the methods, what we could do is having, or do we actually need, I mean, if we watch on them, we can also use that, right? A home view provider. But I think that wouldn't be a good option. So what I will do is view provider, and we would just read on it. And this view provider, can I access that now from the part where I need it? So like here. The argument cannot be assigned. Okay, that's fair enough. I mean, home view provider. So, and here of course we have to change it then too. But yeah, so we get now the information, have that now in place. And here of course this is now the home view provider. Cells isn't defined for the class search control implementation. That makes sense. Oh, a lot of errors. Okay, yep. Yep. Because we don't access that, we have provider.cells now. And provider.cells again. Okay, that was a bit too much, unfortunate. This is unsafe to do, so instead of considering context watch, if you used context reads voluntarily as a performance optimization, the solution is instead to use context select. Okay, probably I used these cells wrong, so we just we still want to have the cells here, and we want to pass in the home view provider. So you get the list of cell states and the home view provider cells. Try to use context read inside either a build method or the update callback. So. Okay. So, and the goal that I wanted to achieve is actually that if we receive here finally that provider, and now whenever we take a specific node from the frontier, we explored, we make it empty, we remove one. Now what I want to do is I want to color that node that we are on. So I guess what I could do is now access the cells from the provider. Cells or update cells. I give a node dot state, and the new state is, I don't know, cell state visited. Yep. So this state does not exist yet. Visited. And now inside of our home view on the bottom where we, no, I think we have a widget for that, the cell, we color that one, right? So that means one of them could be our new visited, which returns the color yellow. So until now everything is green, so let's try that and start. Aha! Okay, it's super fast, but right. He found the best path to these two locations. So we can now color that in. So the only problem that I have, it's still a bit too fast. So maybe what we could do is await future dot delayed duration of seconds 1. So what is that as map for each area? That's okay. Start DFS is at the moment, it's wrongly implemented, of course. Yeah, so we have to say this is a future of tuple 3. So, and here at this point we have to wait for it. So recreate everything. We create a starting and an end point. And let's start. Okay, so we can directly see now that our solution did not work that well. Okay. Wait. Okay, that's maybe not too bad. Look at that. So we need 42 steps and we are jumping all over the place. But actually, if we look at that, these are just less steps, not more. So he identified that the easiest way is somewhere here on the field, and he gives us the information what is the easiest. So that means we can now make that colorful, we can play a bit around. So the next step would be that the solution, the final solution, should be also in a different color. So, and this happens when we receive our solution in the impl. That will be this part. At the moment we just use this part here, but what we want to do is we want to color that stuff inside. So we have the provider, we use our cells, and what we need is the node.state, and that is equal to cell state solution. Solution. And inside of our home view provider, home view, I'm almost, well, not done, but we are coming closer to a good solution, or at least that we can see the good solution at the end. So we have the start DFS, we run all that stuff, we have the implementation, we color that into solution. Oh yeah, and my goal was now that create another one, solution, and this one is green. So all of that is solution. That is wrong, I guess. Visited. No. Wait, this has to be yellow. And I see right now that green is already done, so let's take blue for it. And let's be honest, blue is always the solution. So red start, we have a play button, we have the end, and we play. So Okay, I think the logic for our neighbors is still wrong. That's the reason why we are taking this weird step approach here. And what didn't work is the solution. So, and the actions are right, up, right, up, right, up, right, up, right, right. Why don't we pass that correctly? So in the search part here, we don't update. Yeah. So what we have to do is provider.update cell. The index is the node.state, and the new state is cell state.solution. Okay. Hot reload. So if I have my starting point here and my end point here, and I don't know, let's create some walls here. Papa, not too bad. So right. Okay. Was it just luck? So if I restart, what? Ooh. It needs a start or end point. Okay. Because it changed now the values here. Yes, a line in the middle and then try. Okay, so that means here. And I don't know, here, and then we block, right, by drawing one line. And I think he should now search everything on the left side. Oh, okay, good. I think that was the problem with the neighbors. Hey! Okay, so we found another bug, I guess. On the other hand, I didn't specify that the walls on their side is not possible to cross, so it's actually pretty good. Sorry, I like that too much. Okay, cool. What I would like to see is that we ignore the last one and okay, so if we reset now I have to do something with the neighbors, right? Because it is not possible that someone who is here takes this as a neighbor. So if you start here, this on the side shouldn't be a neighbor. So where is our neighbor? So as you see, if you want to make one step to the left, currently we say you can go here and then you make one step to the left, which is up here then. This is not good. We have to make a little bit modulo things, I guess. So this starts at 0, right? So 7, 14, 21, 28, 35. So that would be the state. Okay, so if start is at 1 and end is at 16, then it will give you approach in one step. 1 and 16, yes, exactly. So at least this is what I would expect. So if I start here and here, would say start. Of course he needs to find it first, but yeah, actually it should. Here we go. So it went there and go one step to the left. And what we also see, it doesn't take necessarily the optimal path, right? He just gives us the first path, which is interesting. Actually, I thought he would check all the things until So it just finds one path, not the optimal path necessarily, right? So if I block this a little bit and would do this parts, so let's see. Ah no, this way it can't work, that's true. So we have to do it this way. So game over. Okay, so the idea is to take it modulo 7, and if it is null, modulo 7, is that right? No, modulo 8, and if it is null, then we want to throw. We get the current state modulo 7 equals null. Yeah, then it's not possible. Is this the right part here? No, I think this is that part here. Or when do we remove it to? And now I think it drops on our feed that we didn't decide to make it a row and column approach. So because the state itself is not taken into account if it is already existent, what we could do is say, okay, if the state modulo 7 equals to null, then we say that it is just a state, else it is state minus 1. And if the state modulo 7 equals to what is that? 0, 1, 2, 3, 4, 5, 6, 7. So it should be 7. 7 modulo 7 is 0. Wait, what I'm doing. So this is 0. 0 modulo 7 is 0. 7 modulo 7 is 0, and so on and so forth. But is this 7? This is 8, right? What I'm doing, so okay, think before you work. So 7 modulo 7 equals null. So that is the point here. And here, because 0 modulo 7 is also 0. So this here is 8. So everything, so okay. And 8 modulo 7 is 1. And from here to left is not possible anyway, so it only can go from here. So that's the reason. So state modulo 7 equals to 1, then we return the state itself, or state minus 1. Else state minus 1. Good. And the same thing happens here. So if we say that the state modulo 7 is equal to null, that means we are on the right side now. Then we return the state or state plus 1. Is that correct? So if I'm right and I want to go to the right, let's try it. So we had this part. and in our case it should be possible now. Whew. Sorry Minu for whatever happened. Okay, that didn't work well. Okay, so it seems that I make a mistake somewhere, so let's think about it. So if I make state -1, I don't know. You got Streamlabs was calling you for spamming symbols. Don't know what you have done actually. Okay, so we find an optimal or we find a path, and you got blocked again. How do you wait? Should I maybe check the Streamlabs settings? Hup. Every time something else with these stream stuff, you cannot make a formula. A formula. Yeah, that could be that it uses that as weird messages. Let me check if I can set up the CloudBot. So I will remove that quickly. So try again. Aha. 7 times n plus 1. Okay, wait, here. So you mean we have this formula more or less 7 times state plus 1, and then we say this is 1. Else we return the state itself or state -1. Or actually, what we want to return then is that left -1. It's not possible, so -1 it should not be possible, and we return it. I think that's better than the state itself. The current block. You mean the row at the end, but the problem is we don't have the row, right? Wait, stop. I have to think. So if I say 7 times the state, so the state can be anything from 0 to 63. And I want to say that you cannot pass the left border. Then I want to say that you are not allowed to go to 36, 55 from the left side. So it's impossible. So when can I go to the left side? You forgot mod? Yeah, but still, if this is modulo 7, then let's assume we are here. So okay, we have this. We have 0, this would be 8. 7 times 8. Let me just think quickly, or let's calculate. 7 times 8 is 40, is 48, is 6 for 56. So we have 56, and we say now +1. And now we would say we divide it by 7, and we get 8 times. But we say modulo, then we would have left 1. Okay, it could work. So, and if this works, then we could do the same thing for this part here. But still, why should I make it times 7 and then remove it again? Yeah. State plus 1. State plus 1. Okay, I'm not completely convinced, I have to admit. Let's see where we come to. So we have this, and we have this, and we build our wall. Start. There is no solution, but he didn't check everything. Ah. Wait. No, stop. Okay, so we have some bugs, I guess. So we have an end, start and an end, and then we block the way. Start. Ah. Okay, so I get the idea. The problem is with that +1, which is good, but with this +1 we kick out this whole line here on the side. If I understand that right. So if we use that, we have this guy and we have this guy. Yeah, so you see this one is not really a field anymore. Wait. So if we remove that, and we have now, for example, the state, which is, as I said, let's think about it, 0, 7, 0, 0, 8, 16, 24, 32. So 7 times 32 plus 1 divided by 7, which gives 1. Yeah, maybe I have to increase it to 8. I think that sounds more reasonable. And then plus 1. Mm-hmm. Okay, but here we can really see the DFS, right? We go all the paths always till the end. So, and it crashes again. So we need a +1. How about if we times 7, but then we... What happens is that the left bar is not used as an element anymore. Ah, because I say 1. Maybe it needs to be 0. Wait. I think that makes sense. I think that makes sense. So let me think. If we do that and restart. So we go here and we go here. Start search. No! Okay, stop. We are just guessing. That's never a good option. So let's think that, oops, Don't destroy it. Just think about it quietly. So, one node. What we want to achieve. So, new. Perfect. So, I want to draw something. We have a pen. So we have some column with different numbers, right? Let's say 3, and we have 2 of them. So this is 1, 2, 3, or better, let's do it with the right values. This is 0, 1, 2, 3, 4, 5. Okay, so we have that stuff. So whenever we are at a 3 or a 0, we are not allowed to go to the left. So not allowed to go to the left. So that means whenever I have modulo 8 in our case, right? Because this is actually 8 here. And this is 0 in any case. So if modulo 8 equals 0, then I'm not allowed to go to the left. And the same thing on the right side. So if I have 8 minus 1, which is 7, right? So plus 3, exactly, which we... And if this is null, then I'm not allowed to go to the right. So that would be this current state plus 1. So this will be also... How can I define that? This is always exactly 3 points, so that will be 8. So 7 modulo 8 is that point, right? We have 7. And it will be always 1 less than the calculation. Yeah, perfect. So that means what we have here is, for example, 7. And then we have modulo 8, which will be 1, is not allowed to go to the right. So let's start with that, because that is pretty clear, I guess. So we have the state. And I think we don't necessarily need that, because the state modulo 8 is 1. Wait, that is the wrong side, I guess. So we remove that for now, sorry, just want to try. So this modulo is 1, then we are not allowed to go to the right. So if this is true, then we give -1, else we improve by 1. What is the first state value? That is 0. So actually what we have here is 0, 8, 16, and that would mean this modulo 8, right, is equal to null. And if this is not the case, then we are not allowed to go to the left. So that means if we remove that and we have state, which is modulo 8 equals null, then we are not allowed to go to... I think I've wrote that once already. So state is equal to, and we have -1. So start and endpoint and broken dreams wall. Fingers crossed. Looks good at the moment. Huh? Huh? Okay, now this is different. So this is now for him a blocked path. He cannot move there. So it seems he is not allowed to go to the right out of some reasons. So state modulo 8 is 1. It's the only reason why he wouldn't be allowed to go to the right. State modulo 8 equals 1. State modulo n equals null. And what do you mean with don't -1 -1? I think we... Yes, so we do that, right? So state divided by 8 is equal to 0. That would be this line. And then we are not allowed to move to the left. And state modulo 8 is this line. I guess -1 just means we are out of the value, right? And we are not allowed to move to the left. What? Only up to... Yeah, but this is exactly what we are saying here, right? So... Okay, let's get me a new starting point and let's see what we get here. So up, down, left, right. But as you can... only up and down at 8 minus goes to 7. Sorry, Minnow, I'm not getting completely clear what you mean. Is don't -1 is not to move to state -1. So this means this is the OR part, right? So if we have 0 at the place, we give -1, which is out of the value. So it will be removed from the result. Or am I wrong? So at the 8 box, okay, so we are at the 8 box, which will be this one. Then -1 as per your condition, that means it moves to 7. No, that is this part here. So that would mean state modulo 8 is 0. Then the true part is -1, right? So -1 is just meaning that left -1 is... wait. No. If -1, then we wouldn't be able to go to the left. So what I can try to make that clear, or if this is true, then we will take that here. Okay, now I'm able to have multiple start points. That's also new. So let's do it this way. And what I want is just to print a little bit this stuff. So this is now the only possible way, right? He needs to move to the left. So, and you see, he cannot find the position. So that seems to work correctly. So, and now the opposite is move to the right. Right? So that would be modulo 8 is 1. It's -1 or state -1. Okay, so clear up. So we want to go and be here, and the endpoint is here. Finish that all. And start. And he finds that because right is 16. What do we print here? State modulo 8 is 14. So state modulo 1 is I'm printing state -1. Yeah, but why is the question, isn't it? I get false, I get false. I get false. This is true, right? Ah. Okay, that's the reason. So they have to... So I have the start point here, I have the end point here. Crash, no solution, fantastic. Okay. But now why do we, probably because of that reason, right? So if I have here the start point, here the end point, I make some funky wall between them. So. Okay, better, but we still don't crush this line. We cannot move further than that, and I can't neither, so that's weird. Okay, -1 is just the value that gets removed, right? So everything that is not higher than 0 is getting thrown out of the list of the results. So we have state modulo 8 is 0. If this is the case, we return -1. So that means if we are at this place here, we return -1, so we cannot go to the left. It's impossible. Then to the right, we say state modulo 8 is 1, which is this part or not? The box numbers, yes, 0 and 63. Ah, the print, yeah, sure. So let's do that. So we have the state, which is the state itself, and let's see what happens inside of here. So we have that, and we start our search. Well, of course, we have to clear, creating a win and this, and a wall. Why do we get twice the information? So let's run it through quickly and then search one of the elements. So for example, this one. So we know this is 63, 62, 61, 66, 59. But why is it twice? That is the first question. So we have the state and this neighbors class. What? Oh. Yeah. Okay, what was that? that here and up and run. So the good thing is the first logic seems to work, so it doesn't try to navigate to the left. But why is that wrong? So as I said, we are 63, 55, 47, 46, 45, 44, 43, and 42. So if we search for 42, 41, probably, no, 42. He says the left way is 41, but he don't find the right one because he says false. You got it, yeah? So let's see, where are we? He says that 42 divided by 8 is false. That's good. But if this is false, no, that makes no sense. Find a way. When it finds no way, then it tries to reach the... Yeah, that's true, but it should be added to the frontier, right? Slowly, I have to think. So let's see. I think this was right. So if this is 8, then it should be -8, -1, and then it should be state +1. So that would be on that side. Let me think. So we are here. We are not able to go right. Okay, fantastic. We know that. So that means this logic actually seemed to be correct, in my opinion. So let's see. I click here. I give it a new color. So we fill up everything here. The only problem is if we turn that now around and I put here my green one and here my red one, give some walls. So that means something else is completely broken, right? So the third step is the problem. Let me... Do we get the number of steps here? No. So let's see. We have the state index 29. So that's the first one. Then we have 30. This is this one. 31. And we get always false. So why is that 31? 32. 33 and then 41. Okay. So that means this guy here but the color change has no impact on the behavior. The problem is more that if I see now 31 divided to 8, this is 7. Let's see. So this is 0, 1, 2, 3, 4, 5, 6, 7. 7, 14, 21, 21, 28. Why is it not 28? Because it's 8. Because it's 8. So this is 7, this is 15, this is 23, and this is 31. That's the reason. And 31 is 7. This is not 1, this is 7. If the path is not found, it shouldn't search any further, so it throws an error actually. So it should go through each of the tiles, and at the end it should throw an error. Ooh yeah. Ooh yeah, we get our error. We are there. There is no solution. Ah, yes. Ah, fantastic. Okay, so that means finally we have that and that. So if I click here now and I create that now, it shouldn't search anymore in any weird circumstances. Can remove the prints maybe in the between. Okay, can you please place start at 9 and 14 and make path of 2 blocks width? Okay, let's do that. So, and the path was wrong, I guess. Oh, that would be sad. Okay, but let's search. So you say that if I place the start at the 9 and 14. Go, 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 start up. So we have here 7, right? 14, that means, no, that 7 plus 8 is 15, 14, 13, 12, 11. 7, 8, 9. So the start you want to have here and the end at 14. So 7, 15, 14. And then you want to surround it with 2 like this, I guess. No? Okay, not like this, but close. So, and then in middle, so like that. And 2 blocks, like that. Okay, start. That's exactly what I would expect. Okay, with that we have now, the problem is the pathfinder. Why? It was continuing. Ah, you mean that the frontier is taken wrong, because it starts to make these waves of lines. It's a good question. But so wait, if we have something like this, maybe like this, and then we would have a path that goes here and another path that splits up here somehow, like so. Blocks, open up that path like so, creating this maze, kind of this, maybe doing so. And we would have here our start and here our end. No, it looks correct to me. no, that looks kind of like I learned it in the session from the CS50 group. I'm really happy with the coloring and everything, really cool. The only problem that I currently have is that I cannot start again from the beginning. That I don't remember the end and start date. Chill. Okay, no, that's good. I mean, that looks quite good. So we have a maze, we can do that. And now, if I have understood everything correctly, and then let's go to the search impl once more. And here we do, of course, a lot of stuff. But the only difference between the start DFS and the start BFS should be that this frontier is now a queue frontier. So I will call that now start BFS or DFS, and I will pass in, I don't know, just a bool DFS. First search. And what I want to do is here to give that a stack or a queue frontier. So, and then, yes, that was DFS. So that was a deep first search. So, and now we will, because it was going to the end of the point and then it goes to the next. But at BFS, at this point, it would take this, and then this and this, and then this and this, and so on. So let's see, that is BFS or DFS. Or start search, kind of this. So but to copy everything over would be ugly. So let's keep it with that. Start search. Don't know what you mean now with a high time complexity, but could be. I don't know. So we have that. We have the deep first search. Explored tiles is 0. So what is high time? We have that. And now I wanted to deep first search. Ah, yeah, exactly. So we have that. In our impl, we have this now with the boolean of deep first search. Yes, that is for sure. But what I want to do is to implement all of the 4 best possible solutions, and then the user can decide what he wants to use. And if it takes long, well, it's his choice more or less. Start search. Now we can pass in, for example, that is true, and in this case it would be false, right? So okay, so I select now breadth first search. More or less we have to recreate our maze like so and like so. We do this. Up. That was wrong. Ah, sure, I can do that. Yep. Working all the time with that and didn't know that. So where's my webcam? Here we go. Bloop. Bloop. Maybe like that at the moment. So okay, but in the meantime I draw a little bit more. So, and I would keep it like that. I think that was good enough. And here we had a second line, I guess, with this separation. No, exactly the opposite. So, and now if I run the breadth first search, now at these points it should now take both of them. one after another. First this, now this, now this, now this. Ooh, yeah, it works. Ah. Completely left is even better. Yep, because there is just the text, but what? In the meantime, while this is anyway moving around, put that on top here, maybe make it a bit smaller. Fantastic stream labels. Oh, that was not a good idea. Up, up. So, on the other hand, I can just make that smaller and push that also up, like so, and then I can bring back my webcam where it belongs. Oh no, it's still not enough. Like so, and then I can take these. Setting up the stream on live, that's always the best. So, anyway, kind of like that somehow. I don't know. Then we have the app on that side, so a lot of space, and we can select the breath search, and we are fast enough, and we are getting better with that. All right, so I think that was quite a success already, right? So what I want to do is I will create a little video for that because I really love that this is working that fine. And the A* search or the GBS is a little bit different now because they use the first time heuristic, right? So this is greedy best first search, this is that one. And A* search is using the cost to move somewhere plus the, what was the idea? The cost to search somewhere or to go somewhere and the heuristic together and calculates the values then. Yeah, but I think we came pretty far with our maze, and what I would like to do for the next time is maybe improve it even further by giving it a bit more coloring and maybe... No, we haven't implemented GBS at the moment. It's just DFS, that is the only thing that we have implemented yet, and BFS. And the next step is GBS. And the last thing is if I try to do that, you see unimplemented error yet. As I said, it's a learning path for myself for the learning the algorithms, because I have no idea about the whole search algorithms from the AI course yet. So, but with that in mind, what I want to do actually, that I forgot the last time, is to push that whole thing into GitHub. So, do I have to do that? I don't know. So VSC, let's first, no, I want to activate that. Apply it, import. Flutter is the origin? No, no, no. Not in the slightest. Okay, anyhow, I think I will have to do that later, but I will push that on the GitHub repository and then you have access there if you want to. Then you can also use that. No. Okay. All right, so thank you very much for watching today. I think we came quite far, and what I want to do is just make that once more in full screen. No, that's a bit too big. Yeah, like that. And in the meantime, we can use cap, I think, and just create one last maze, like so. Maybe do the starting point here. Endpoint will be down here. So what I learned today on the stream was to identify how we get the different parts implemented, also how we can set up that everything works also in Dart the same way, that we can use it there. I learned about the tuple free representation, that is a package that we can use, which I really like. Another thing that I learned is, again, how we can set up this implementation. So to identify, okay, how do we see these different DFS, how you can create this algorithm, how does it look like? And last but not least, what I really enjoyed was to see, or what I don't really enjoy it, but I'm happy that we solved it, is that we see how we can color, how we calculated the neighbors now with that one value. Yeah. Just make a docs and share the link. Oh yeah, that's a good point. Okay, so but back to this, I want to add here the maze search AI and start the search. We don't have that, but we can have brief first search. From that second, of course, because I set this delay. I want to see how it calculates, you know. So that was, if I close that now, as you can see, we have here that delay. We created that. If we wouldn't have that, it is super fast, I guess. So if I now start something like that and say go, you see, in seconds. Maybe I should give also a screen of this. Yep, and now start. And another thing would be the start here, the end here, deep first search, and go. Okay, but enough is enough. Thank you so much for watching. It was fantastic. I will try to do all that stuff, Minu. Hopefully I can get the time to do it. And then let's see. Else, I wish you a pleasant day. And we will see us maybe tomorrow if I have the luck and the time to do it. So, see ya.